Hi everybody, this is David Paul, and today we have the first of a two-part series on degasification. This one today is on forced draft degasification, and then 2 weeks from now we'll have one on membrane degasification. So the way the webinar will work, we'll have 40 to 45 minute presentation maximum. I'll start out with an introduction, and then Tony DeLoach will be providing the details on forced draft degasification. And then we should have 15 to 20 minutes for question and answers. Just type your questions into the question box or the chat box, and we'll get to that at the very end. This presentation is recorded, and it'll be available here in 2 to 3 days at this location, this URL. You'll be sent a thank you email tomorrow, the next day, and it'll have a PDF of this presentation, so you won't have to take a lot of notes. So just so you know, DeLoach Industries and David H. Paul Inc. do not have any financial relationship, so no money transfers here. We just present this because we think it's an important point for the water treatment industry. I've been in high-tech water treatment a lot of years. Been hundreds of plants since started this company 30 years ago, and have a Master's of Science degree in microbiology. Tony is the president owner of DeLoach Industries. He's a mechanical and process engineer, degree from the University of Florida, and he holds 5 US and international patents, so he'll be doing most of the talking today. I'm just giving a really brief introduction. Pre-RO is not, degasification is not that common. The only one that I'm really aware of is the high efficiency RO, the trade name Hero system, and I'll just mention that briefly here at the end. Post-RO is common. So it's real common if you want to reduce the loading in feed water to an EDI unit or a mixed bed ion exchange unit. So you can reduce gases down to just about whatever you want using the proper technology. So I'll just again introduce the different ways of degasification. Start out with an overview. The amount of gas that will dissolve in water is proportional to the amount of that gas in the atmosphere in contact with the water. So if we have a water here that doesn't have any gas in it, and it was in contact with the atmosphere, well, the atmosphere, has a lot of nitrogen in it, has a pretty good amount of oxygen, and not too much anything else. So by diffusion, which is just random motion from areas of higher concentration to area of lower concentration, dissolved gases will diffuse into the liquid. Well, degasification just means that we need to modify the atmosphere in contact with the liquid so we can get molecules to go from the liquid into the atmosphere. So in this case now we have a water that has a lot of dissolved gases in it, and we have no atmosphere, so we pulled a vacuum. Well, in that case, the gases will diffuse from the liquid to the atmosphere, and if we keep pulling off that atmosphere, then we can keep pulling gases out of the water. So obviously, it would be much quicker and easier to remove gases from water if the water is a very thin layer so that the gases don't have far to travel. So your degasification towers are going to usually have a spray system and a packing like balls or saddles or something where the water hits this packing material and forms a very, very thin film of water. And now the gases in the water don't have very far to go before they can escape. So forced draft, that's where we're taking atmospheric air. So air, the air that we live in and breathe is 78% nitrogen, 21% oxygen, and just 1% of everything else. Most of that is argon. So there's just a very little, proportionally very little amount of CO2. So if we had a water that has, let's say, high in CO2, we can just blow air across the surface of the water, and the CO2 molecules will diffuse out. So we can greatly reduce the amount of CO2 in the liquid. So a forced draft degasifier, typically you have the spray system and the packing material, and then you have an air blower that blows air up, and that then allows the atmosphere to come in contact with the liquid and the dissolved gases to escape. Vacuum degasification, kind of the same thing, only we're pulling the atmosphere away. So you can still have, you know, the spray system, the packing, but now you can get to low levels of all gases, including oxygen and nitrogen. And then lastly, membrane degas, that'll be the webinar 2 weeks from now. The membrane itself is hydrophobic. It is not a water transfer like an RO membrane. RO membranes allow water to go through. Water does not go through a degas membrane, but dissolved gases can pass through. So this is just a picture of what we'll talk about in a couple of weeks. So the inside, where you see the nitrogen, this is, and the black lines are the actual membrane. Well, if you load up the inside of these fibers with nitrogen, then by diffusion, nitrogen will go out of the fibers, but CO2 and oxygen will go in. So you'll be able to get CO2, nitrogen, and basically anything else to very low levels. If you pull a vacuum, then you take even the nitrogen out. All right, so before an RO unit, like I said, is not common. The only one that I'm aware of is called the HERO system. It's used, it was actually invented 20 miles from where I live by Intel and a consultant because of high silica. They wanted to go to very high recovery on high silica. So they remove all the hardness and alkalinity. The alkalinity, if you acidify the alkalinity, it turns into CO2. And the decarbonator, which is a forced draft degasifier, or could be a membrane degasifier or vacuum, but more commonly a forced draft. That's in front. Then you can go to very high pHs because you've removed the calcium carbonate scaling potential, and now you can go to very high recovery rates and high pH. Post-RO is common, so just give you a couple of examples. Here's power generation, where we have a multimedia filter, heater, cartridge filter, RO, tank, and then a decarbonator. Usually these are forced draft, and then it's in front of a mixed bed ion exchange. And the last example is for microelectronics. Not showing, I'm only showing the very last part, the highest purity part of the plant, where they have a membrane degas downstream of ozonation and 185 nanometer UV. The ozone enhanced 185 nanometer UV is what it takes to get down to, you know, a half a part per billion of TOC. But the ozone then is converted to oxygen, and have to get rid of that oxygen or it would ruin the microelectronics manufacturing. So they use typically membrane degas in this application. All right, so that's it for the introduction. And now Tony DeLoach is going to give a presentation on forced draft degas.
Hello, everybody. I'm Tony DeLoach, and welcome to the presentation. David, thank you for the introduction. I'll quickly go through some background slides and make sure everybody is on board now, and hopefully everyone can see the screen. So forced draft degasification is the topic of the presentation today, and there, as David mentioned, there's various types. There's forced draft and induced draft, vacuum, steam degasification. So today we're going to be focusing on just forced draft degasification and some of the benefits for pre and post reverse osmosis treatment. Introduction, as I've just gone through, our business started in 1959, so the company began 60 years ago in Sarasota, Florida. We're a designer and manufacturer of water, wastewater, and air emission systems. The founder was my father, Walter W. DeLoach, or better known as Bill, and pioneered some of the first systems in the area of reverse osmosis and forced draft degasification back in the days before membranes were even in vessels. They were just loose. So been in it for a long time, and you learn in this business by trial and error and by practice and surrounding yourself with other smart people. So I think I've been very fortunate to be around a lot of talented people like David and others. My goal today is to talk about the forced draft degasification and the benefit it plays in the pre and post treatment of reverse osmosis. I'll go through some of the background terms quickly, the methods, some applications for anyone new to the industry, and then move into other topics. The presentations tended to be informative and discuss kind of a wide range of the topic quickly, and hopefully provoke some questions at the end, and maybe give everybody a little different perspective on the applications and designs and uses of forced draft degasification. Thank you. I hope you enjoy. So let's take a look at some of what we will discuss during the webinar. Quickly cover the types and terms used to discuss forced draft degasification. We'll review industries and applications for forced draft degasification. We'll answer a trivia question, maybe one or two of them anyway, and review some key components of what make up a forced draft degasification system. And we'll drill down in some of those ideas. And then we'll review the why forced draft degasification is a benefit for pre and or post RO. We'll look at the factors needed to design a forced draft degasification tower properly. There's a lot of variables, and there's a lot of different means and methods, and obviously different companies manufacture their systems differently. And then we'll learn what is hydraulic load and loading rates, and when is enough. So when applying hydraulic load into a degasifier, when you get to a failure load through hydraulic flooding. We'll discuss pH and the relationship of degasification and solubility of gases. And we'll learn how to adjust pH with forced draft degasification. Select one component during the design over another component. And then we'll learn why and when to use round forced draft degasification towers versus square, when to use random packing versus structured tray packing for degasification. And then we'll examine things like mass transfer, HTU, NTU values, and other technical boring stuff related to forced draft degasifications, towers and their designs. So we'll try not to be too boring, but I want to give everybody kind of a broad range of information. So what is degasification? Degasification is defined as the removal of dissolved gases from an aqueous solution. It's commonly utilized in the process and purification of water, but it also is utilized in the process of solvents and other chemicals. We will be focusing today on the most cost-effective water degasification process that's commonly called forced draft degasification. And forced draft degasification utilizes a process called pressure reduction, as David mentioned. It relies upon mass transfer and the solubility of a specific gas at different temperatures. So I think you saw a slide similar to this at the introduction, but you'll see gas, above and below in a liquid phase and dissolved gases. And this will be CO2, H2S, and you have dissolved. We have this in the air, or it can be an induced situation. So in a chemical process, such as a refinery, and many times some of the process applications create the condition that have increased CO2 or H2S in the liquid phase. And then the pressure reduction, again, mentioned by David, we're going to lower the pressure reduction in degasification to allow the dissolved gases to travel to the lowest pressure and then to be stripped or removed. So of course you end up with a process of liquid with less gases in it, and that can be taken to the far extreme of 99.999% removal to 100% in some cases, just depending on the need of the process. So air and water process flow in a forced draft degasification. Air produced by a centrifugal blower or pressure blower enters the tower at the column at the bottom, and this is called a forced draft situation. If the blower is mounted on the top, it would be called induced draft because it's pulling air. But this is a forced draft degasification. The air driven by pressure travels upward towards the exhaust and then exits out of the tower. And in between, you have things like the packing, media packing, packing support plates. Water enters at the top of the tower column, and it travels by gravity, and it's dispersed by the distributor over the top of the media bed. And we'll get to that and some more details on some of these key components here. The water travels downward by gravity over the media bed, and its specific weight encounters cross-current airflow. This is what causes the stripping and the lower vapor pressure conditions. So some basic terminologies and definitions for forced draft degasification. And David touched on some of this, but Henry's law is a key law that's used in the design of degasification or air stripping. It's a gas law that states the amount of dissolved gas is proportional to its partial pressure in the gas phase. Proportionality factor is called the Henry's law constant. So this is something that we all learn in chemical engineering and some of the basics in water chemistry. The mass transfer, the movement and transfer from one location to another. So for our application, the transfer and movement of dissolved gases is how we're discussing this today. The distributor or distribution refers to the method of how the water enters the tower and is distributed over the media bed. There's several types of distributors are manufactured for forced draft degasification towers, and we'll discuss probably 3 or 4 of them today. Media or packing refers to the internal loose, fixed, or tray packing that is located inside of a tower, comes into direct contact with the water, and the media is sized and selected based on the specific gas and concentrations to remove. You heard the term a little earlier, H2U or NTU. H2U means the height of a turn unit, and NTU means the number of turn units. So all media packings have a value for different H2U and NTU values, which are utilized in the calculation of gas transfer. An HETP means the height of an equivalent theoretical plate. Again, it's part of the science of calculation. And then controlled film refers to how water is shaped and reshaped over a thin layer to allow gas molecules to reach the water droplet edge for removal. And then impingement is another process which refers to how the water is shaped and reshaped by fracturing the water to allow gas molecules to reach the water's droplet edge for removal. So here's a trivia question for everyone who's online. So when did the first forced draft degasification treatment system begin for the first municipal reverse osmosis process in the United States? It was first developed and deployed for the municipal reverse osmosis industry in 1976 and placed into service in 1977. I was actually on this project at that time. 2 forced draft degasification tower systems began processing water that was produced from the very first municipal, so it's the very first municipal reverse osmosis water treatment plant in the United States. It was located in Cape Coral, Florida in 1977. The towers are 12-foot diameter, 12-foot tall, and they were initially designed to treat 3 million gallons a day. The plant, of course, has been expanded multiple times since then and has grown exponentially with the development and increase in population. So industries that utilize forced draft degasification: aquaculture facilities, industrial water treatment facilities, municipal water treatment facilities, petroleum refineries, and wastewater treatment processes. So why is forced draft degasification utilized? Hydrogen sulfide and carbon dioxide, of course, shortens the life of boilers and tubes and causes corrosion. Industrial applications, as David mentioned, and refineries utilize degasification to remove CO2 and hydrogen sulfide prior to water softening that causes ion exchange, like cation and anion systems damage. This extends the resin life bed by reducing regeneration cycles and also saves, of course, chemical consumption on the regeneration and operating costs. So you can look at degasification in this application for 2 processes. One, it lowers operating cost of the overall water process, and number 2, it preserves and saves the life cycles of the resin beds. In addition to boiler feed processes, water is utilized at refineries and industrial plants for other uses, such as manufacturing of chemicals and materials, and even for the cleaning process. So the semiconductor industry, David mentioned, is one of them. It utilizes water for both manufacturing and also for the cleaning of microchips. And so in that case, of course, it's ultra pure water. Benefits of the degasification pre and for reverse osmosis. As David mentioned, very not as common as you'll see it in the pre-osmosis. The areas that we see it and are asked to provide systems on most often, if the supply water for the reverse osmosis application contains contaminants such as chlorine, and some processes utilize city or county waters that might have chlorine, then it's of course detrimental to the RO membrane elements, and sometimes degasification will be used to remove the chlorine prior to going through reverse osmosis to prevent shortening of the life of the membrane. And it's also can be utilized for removal of ferrous iron. Ferrous iron is oxidized to produce the ferric iron and then can be filtered pre-RO, increasing production rates of the RO process. Forced draft degasification can also be utilized to help remove harmful levels of manganese. The manganese oxidation process works at higher pH levels, so the removal of carbon dioxide helps raise the pH and then begin the process of oxidation. Last, for all of us that are in this business, remember the objective of reverse osmosis and other water process designs should be to maximize the quality of production of volume of finished permeate water while minimizing the short and long-term operating cost. And I think that's one of the key factors in good design, is that there's a lot of ways to do reverse osmosis, a lot of ways to manufacture process equipment, but the key is to design it at the most lowest operating cost for the highest quality water. So the use of forced draft degasification tower is the most cost-effective way to accomplish these objectives. There's other ways to do, as we mentioned earlier in the presentation, degasification, but it's about cost and operating cost. So benefits post-reverse osmosis. Majority of degasification systems for municipal applications are for post-treatment and also for industrial, I'd say. The use of degasification post-reverse osmosis is applied to remove in-train dissolved gases such as hydrogen sulfide, carbon dioxide from permeate water. Because the RO membrane, of course, removes the solids, but anything that's dissolved or in the dissolved phase, RO does not remove. So water prior to either further treatment, ion exchange softening, or chlorination, or for storage for use. It increases the pH without additional chemicals by removing CO2. So by liberating the CO2 out of the water, you can typically raise the pH points between 1 and 1.5 levels after post-degasification. Removal of hydrogen sulfide prevents corrosion, improves the water quality and taste, of course, and reduces chemical costs. So disinfectants like chlorine, sodium hypochlorite, or other oxidants will react with any of the remaining hydrogen sulfide in the treated water. So by removing it first, you basically lower your chemical usage costs, and you, of course, improve the water quality. So removing the H2S or hydrogen sulfide gas prevents the increase of turbidity, preventing the oxidation of the sulfides. If H2S is left in the water, of course, it will react and oxidize, causing higher chemical consumption rates and costs, and then, of course, a higher turbidity rate. So your TSS levels will rise. Removal of carbon dioxide post-reverse osmosis elevates the pH, as I mentioned, by stripping the CO2, saves chemical usage of caustic or soda ash, and then operating costs and water qualities are improved. And then removal of the H2S CO2, of course, protects and extends ion exchange resin, as we mentioned earlier, and reduces the regeneration cycles. So what are the requirements to design a forced draft degasification system? Like always on any good design, starting off with a good representative water analytical sample that provides a complete breakdown of the water chemistry, including pH, flow rates are needed to determine the hydraulic load and size of a degasification tower. So you need to know how much water you're going to treat before you can even start the basis of sizing the tower. Concentrations of key contaminants are needed because this information determines the hydraulic load. It determines the type of tower. There are, as I mentioned, there's round degasification towers and there's also square towers. The air-water ratio, the distribution design, the media selection, the depth of the media, or the height of the media, if you would, and the overall height of the degasification tower are all items that have to be selected during items from the flow rate and concentrations. Water temperature is needed because gas solubility changes with temperature. The colder the water, the harder to remove the dissolved gases, which impacts hydraulic load, diameter, airflow, media bed depths. So if your water temperature goes lower, then of course you can decrease your hydraulic load to get higher efficiencies. So that's another factor, but of course that changes your tower size. So you want to find the ultimate design size for the lowest capital cost. You need to know what are the effluent target levels desired in the water. So this too will determine the required hydraulic load, air-water ratio, and the type of media and height of the media, and the overall height and design of the tower. So if your target load is, let's just say it's from 10 to 1, you don't necessarily have to treat it down to 0.5 if that's what the design requires. Other items are needed, such as the location of the forced draft degasification unit, proximity to buildings or other occupants, workers, because if you're removing harmful gases like hydrogen sulfide, we need to understand the impacts of the exhaust. Is the odor control or treatment needed? Is there exhaust stacks involved? Back pressure calculations have to be done. And how does it impact the blower size and the selection and the horsepower? Again, all of this, as I mentioned earlier, goes back into the overall design for short-term and then long-term operating costs of the system. So even understanding if the forced draft degasification tower will have full-time operation support is important. So having 2 blowers and 2 transfer pumps for redundancy may be needed if the unit is remotely located or for a critical process. So components of a forced draft degasifier tower, and I'll quickly go through this for people that are not as familiar. Now this is a forced draft unit that David mentioned had a drawing similar to this earlier. You'll see from the vertical tower, which could be fiberglass, aluminum, stainless, or steel. We actually manufacture out of all types of material for different applications. You have a water inlet located at the top, typically flanged. You've got a blower, forced or induced. This drawing here, of course, in this webinar is about forced draft, so the blower is located at the bottom. A distribution system, and we'll talk about the different types here. This one's shown as a heterolateral distribution system. The media bed, that's in between top of the false bottom location and up towards the distributor. The media support plate, another key element. Again, not only holds the media, but also allows air and channels airflow through the media. Air inlets and outlet vents. Again, if it's an outlet vent, it's a forced draft. If it's an air inlet, typically it's an induced draft. Anchor support, very critical depending on where you're located in coastal regions. Wind designs now are 175-mile-an-hour wind loads. Effluent drain and lifting brackets. So looking at a forced draft degas package system, it contains a degasification tower, a clear well tank. It's usually installed on aluminum or stainless steel skid with a fiberglass grating, mounted pre-wired blowers, mounted pre-wired pumps, and control panel installed, and then factory tested and programmed to run at the desired flow rates and performances. So it can include off-gas odor control for some applications. So let's discuss some of the key components. So a demister, which is located in a degasifier, and how it's used in the degasification tower. A demister is a device designed and constructed and fitted at the top of a forced draft degasification tower. And it prevents the discharge of liquid vapor or droplets from leaving through the tower exhaust that may be entrained in the vapor airstream. Demisters come in different types and shapes. They can be vein type, mesh, coalesce, or any other form of structures that cause the mist to collide and form droplets, too heavy to remain in the vapor stream. Properly designed exhaust systems will maintain certain air velocities specific to the type of the demister utilized by increasing or decreasing the exhaust opening area. Demisters can be polypropylene, PVC, stainless steel, or other non-corrosive materials. So a demister looks like this, shown in the drawing. You'll see the water vapor travels up from the airstream flow, and it's caught in the demister pad or demister structured packing, and then drips back down into the vessel. So airflow contact in the water systems has entrained vapor as it leaves the media bed, and then water vapor travels up to the top of the tower and passes through the demister. And then the demister causes the water vapor to collide and collect increased droplet size and weight. So to what point then the airflow no longer can sustain the weight. The larger water droplets fall back into forced draft degasification tower, as the airflow will not support the weight of the water droplets. So proper airflow velocity through demister is critical. So all demisters have an airflow recommendation in terms of airflow velocity for function. So if the airflow is too fast, it reduces the demister's efficiency and water droplets will leave the demister. Types of demister. This is a structured demister shown on the left. You'll see the chevrons imprinted in the material. This actually causes a twirling action of the air as it goes through the demister. Has a lower pressure drop, one that we prefer, than a pad type. The one to the right is a pad demister. It's made up of mesh, usually laid in layers, and then sandwiched between a top and bottom structure to hold the pad together, and has a higher pressure drop. They both are effective in removing water from vapor streams. The types of distributors for forced draft degasification towers. Distributors are needed in degasification towers to distribute the water over the top of the media bed. So all towers have some type of media, whether it's structured packing or loose fill. Even distribution of water creates an even hydraulic water seal, very critical on performance of a degasifier. So you have a hydraulic seal on the top of the media bed, and that assures treatment for that water coming in contact with the media and also with the airflow. Properly designed distributors will optimize the performance of the degasification tower, enhance the removal efficiency. Uneven or poor distribution of water causes channeling of water and loss of media bed contact, which produces lower performance. So if you have a media bed, you can imagine if the water doesn't initially hit that media on the very top evenly, then you're losing the benefit of that media packing until that water travels down and then is distributed across the packing bed. So tall degasification towers can actually have more than one distributor. These are also referred to as redistributors. They help prevent water migration to the wall of the tower. So if it's a large tower, sometimes they have like wiper rings that help distribute the water back into the media bed. There are several types of distributors for forced draft degasification towers. Heterolateral utilizes nozzles to create proper water patterns and initiate mass gas transfer prior to media contact. Weir or trough type weir distributors utilize a series of troughs to distribute water across the media bed. And then there's a pan type, a pan which is distributors collect the water in a pan and have perforations and distribute the water of the media. And then they have vents that allow the air passage to travel through the pan. I'll quickly show you a little design here of the different types of distributors. The one to your left is a heterolateral distributor, and it's a distribution system. This is a preferred design that we utilize, and I'll get into a little bit of why here in a second. The one in the center is a pan distribution system. Collects the water, and you can see in the top view it has perforations, air vents, pan wall, and so that pan literally just sits there and water enters it, and then it drips down across the media bed. And then the one to the far right is a weir trough distribution system, and that just like it sounds, it's similar to a pan in the sense that it has weir troughs, but the other area is open, so the open source for the air to travel out, but the water flows up and then travels over a weir edge and then is distributed on top of the media bed. So those are the three primary distribution systems that you'd see in a forced draft degasification tower, induced vacuum, or air stripping tower for that matter. So what is the best distributor for a forced draft degasification tower? We prefer the heterolateral distributor, and it provides the highest efficiency for forced draft degasification, and here's the reason why. The mass gas transfer that we mentioned earlier, that release begins immediately when leaving a spray nozzle, because what does it do? Well, it causes both impingement and it fractures the water, allowing the exposed gas molecules to be exposed and to be stripped prior to even first contacting the media bed. So I talked about impingement and controlled film earlier as a terminology, and David mentioned that you want the water spread thinly, and so the thinner the water, of course, the easier for the gas to come to the edge and be stripped away. So in the distribution system with the heterolateral, it actually starts that process immediately, leaving the nozzle even before it gets to the bed. So in our studies, in our cases, this increases the efficiencies in tower and above the normal HTU and NTU values of the media, and our tests have shown between 7 and 18% increase of efficiency, or you can think of it as even a safety net on your design for gas transfer. The heterolateral system provides just a more evenly distribution across the media bed. It prevents evenly and creates that water to air seal, and comes in contact right away with the media, so you're not losing any efficiency of the media, and by avoiding the channeling, and requires redistribution of the water travels down the media bed. So heterolateral systems are less susceptible to fouling and scaling because they're typically designed with a 5 to 10 psi feed rate. They utilize an open or cone type nozzle. Pan and weir types allow sediments to deposit and scale to build. This can cause uneven flow, poor hydraulic balance, channeling, and therefore, again, loss of efficiency. So you can imagine as a pan fouls or gets scaling or plugging any of the holes, then the water tends to go in other areas, and then you get a heavier load in certain parts of the packing and a lighter load in other parts. The types of media packing, there's a variety. I'm just going to show you a few today. This one is called land pack. And you can see it's a perforated loose fill packing. There's PVC slat trays. This is something that we manufacture actually, and there's other types of ones that are manufactured by other people as well. PVC slat trays are used for more heavy fouling conditions. It's a structured packing. There's super pack is another random packing. And there's ratchet rings, which are formerly called tri-pack ring, most people are familiar with in this business. And then there's Q-pack. So these are some of the top media packings that are used in towers designs. And you'll notice that they all have some similarities. One is they all have controlled film surfaces, and they all cause impingement from media to media. So the reshaping of the water droplets, which is critical for gas transfer. Super pack, ratchet, land pack, seal coats, tellerets, and PVC slat trays. Wetting rates and channeling. We'll talk a little bit about the science of getting the water onto the packing. So the wetting rate is critical. The minimum amount of water volume or load rate the media packing selected will perform. Too light a load rate provides poor removal efficiency. So if you go too light on a tower load rate, you'll actually go backwards and have a lower performance in your tower. Channeling can occur in a packed tower. Takes place when the aqueous water solution travels down the column and migrates to the largest voids in the packing. This typically happens near the tower wall or the edge if the packing is not tightly installed. It can also happen if the tower is installed and not level or installed at a plumb. Water can migrate to a wall. And of course, channeling can occur, as I mentioned, at the very beginning in distribution. Redistributors are rings that can be placed every 4 to 5 meters, captures water traveling down a wall to redeliver it back into the media packing. Media fouling, when media packing begins to foul, the water is channeled into the remaining voids. So this increases the hydraulic load rate within the voids. The efficiency begins to drop, and the chemical consumption rises post-degasification until the void spaces become critically limited and the media flooding occurs. So as the fouling gets severe enough, then water will not travel through the media and the tower will flood. So talk a little bit about the hydrodynamics of media packing and flooding. Forced draft degasification towers are designed based upon their need. So the size of the tower, the type of the media determines the hydraulic load on the wetted surface and its flooding limits. So all media and towers have a flooding point. The flooding point varies with the applications and the load rates. Most of the forced draft degasification towers are designed between 15 to 35 gallons per square foot of hydraulic load rates based upon most hydrodynamic capabilities, the HTU and the NTU values of the media packing. Too light of hydraulic load creates what I call dry beds and channeling. Channeling reduces the efficiencies of the forced draft degasification towers. As we talked about earlier, channeling is basically the water's all in one location and not being distributed evenly across the packing. Too heavy of hydraulic load floods the packing and reduces airflow and also reduces efficiency of the degasification process. Slat trays and some structured packings have higher hydraulic load capabilities because they have larger voids in the packing. This makes the media less efficient, lower H2 and NTU values for removal, but also less susceptible for fouling and flooding. And those typical things are used in like high iron concentrations or high H2S concentrations. So hydrodynamic flood curve of packing. When packing is dry, pressure drop increases as the gas velocity increases, as it's a linear relationship. As the gas velocities increase in a wet packing, the quantity of the liquid in the media bed increases significantly as the water velocity rate slows. This changes the linear slope as seen on the right, which is known as the loading point or loading rate, and means when the liquid starts to accumulate and add load to the packing. Increasing the liquid load further, the linear curve turns sharply again until you reach a point that the water no longer can pass through the media and it begins to flood the column. This is called the flooding point. So not very technical, right? Flooding rate, loading rate, flooding points. But this is the curve, and you can see how once you get to a certain point, then it turns dramatically sharp. So the top media performance available for forced draft degasification tower, of course, this might be an opinion, but this is from our own data after doing this for 60 years now. Square forced draft degasification towers, types of media that you can use, super pack, ratchet ring type packing, lamp pack, Silcoat tellerets, and PVC slat trays. Round forced draft degasification towers, types of media, super pack, ratchet, lamp pack, seal coat. So basically all loose fill type medias. Water impact and gas release. I'm going to talk about controlled film here for a second in two different types of packing events. You'll see in the top, you'll see the PVC tray media, and you'll see below just a drawing of a tri-pack or a ratchet ring now. And the controlled film is think about taking the water droplet and spreading it very thin over the surface. So in both types of packing, you accomplish this by having water spread over the surface area and making a controlled film to allow the dissolved gases to come to the surface of the water. In impingement, the different process, this is when the water drops from one piece of media to the next piece of media, and it's fractured. It basically shatters. Well, when it shatters, those new droplets form, and basically the gas, of course, goes to the surface of the water molecule. So controlled film and impingement are basically the two types of technologies, if you want to look at the science behind gas transfer that occur to allow the gas to actually leave the water. So gas molecules journey, as we call it. Water enters the forced draft degasification tower. The droplets with dissolved gas molecules travel down the column and over the media as the gas moves upward against the water flow. So you'll see the drawing to the right, or the little picture to the right, you'll see the gas droplets, and the gas pressure on the outside is less than the gas pressure inside, so the gas molecules migrate to the outer wall. And of course, as gas molecules get to the edge drops are stripped away by the gas molecules inside the drop, and they move towards the lower osmotic pressure. Of course, we help that in the degasification tower by doing what? But by doing impingement and controlled film. So we want to keep reshaping that water droplet over and over and over again, getting those gas molecules to the edge. So to assist the droplets in being turned into you, impinged and displaced over the media surface, exposing even more dissolved gases to the surface. All right, switching gears a little bit, we're going to go into some understanding the pH and its effect on the gas removal within the gasification process. Contaminants in feed water, such as sulfur sulfides, need to have the pH of the water adjusted to obtain full conversion to achieve maximum removal efficiencies in degasification. So water pH adjusted to 5, a level of 5, will allow the maximum hydrogen sulfide conversion. So you can have removals of 99.999% efficiencies can be obtained. So typically we do this in the food and beverage industry, and we do it in some industrial applications. No one wants chlorine or caustic in their beer, so of course you can't add chemicals to do this. So in the food and beverage industry, it's very much, they rely strongly on degasification as opposed to applying any type of chemicals. Reverse osmosis systems often require pH adjustments prior to treatment to prevent scale, but they may not adjust the pH to 5. So typically you'll see pH ranges of, say, 5.5 to 6 prior to degasification. Increasing or decreasing the pH impacts the removal efficiency of the degasification process, as I mentioned. An example is when the pH rises to 7 or above, proper conversion doesn't occur for items like hydrogen sulfide, and the removal efficiency decreases. When using degasification to remove carbon dioxide, the efficiency level of, again, near 100% or 99.999 below detections can be achieved. And degasification post-RO will raise the pH of the water without adding chemicals, typically 1 to 1.5 points. So if you're going through a degasifier at 6, you're going to come out around 7, 7.2 on the outside edge of the thing, and of course saves on chemical addition. So adjusting the pH with forced draft degasification, carbon dioxide is soluble in water and it produces carbonic acid. And that, of course, lowers the pH. So CO2 and H2O equals carbonic acid. And pH can be lowered with sulfuric or HCl acids, which elevates the carbon dioxide levels and then increases the hydrogen ion concentrations in the water. And then removing the CO2 then, of course, reduces the carbonic acid and increases the pH. So it's kind of like reversing what you just did. You're adding acid pre-RO, and then you're removing the CO2 post and removing the carbonic acid in a gas phase. So carbon dioxide gas molecules seek equilibrium. They travel to the outer edge of the water droplet, just as I showed you in that slide before. Surface in the forced draft degasification system. The countercurrent airflow strips the molecules from the water, decreasing the ions. Because carbon dioxide is very soluble, it has a vapor pressure and therefore it can be removed under the laws of govern gases, Henry's laws we mentioned earlier. Calculations are performed utilizing data about the water flow rate, the temperature, the LSI, pH, and the desired removal levels. Forced draft degasification towers designed consider hydraulic load and air, water ratios, temperature, analytics to calculate the removal. And then properly designed forced draft degasification systems, as I mentioned, will raise between 1 and 1.5 points post-treatment. Round versus square. Forced draft degasification towers are available in round and square configures, so why would you choose one over the other? I think I mentioned earlier, I showed you some packing, different slides on packing sizes, but for process water containing high levels of sulfur are not balanced with pH conditions are too high. So square forced draft degasification towers allow the OEM to utilize PVC slat trays. Looks like we're turning over to the Q&A section.
Thank you, Tony.
Thank you.
Appreciate it. We want to make sure that there's time for questions and answers. I think there was a couple of slides that we didn't go over, but as you can see from Tony's presentation, it's very detailed. So when you get the PDF of that tomorrow, the next day, then you won't have missed anything. So we'll turn it back over. Tony will read the question and then he'll give the answer.
Okay, so I have a question. Is it safe to assume that the lower limits of CO2 removal with air is 0.40% or the equilibrium amount? Well, to answer that question fairly, it really depends on the application. But you can definitely take the CO2 removal below the level of 0.040% in a degasification, and it depends on where the water is going to be handled after post-treatment and stored, because as we mentioned, CO2 can re-enter the water as well, just from atmosphere. But you can remove it below the 0.040% level. Okay, you mentioned underloading a degasifier. What's a typical acceptable turn down to maintain design performance? In terms of hydraulic load, I don't like to go below about 18 to 19 gallons per square foot. We can go down as low as 15 gallons per square foot, but it really, you start to then, it varies with the media packing type, and also you need to adjust your airflow ratios. Believe it or not, as you get lighter hydraulic load, sometimes you have to increase your air-water ratio to keep performance. What are the basic efficiency calculations? Well, again, efficiency, that's a broad term, but to do calculations, you need your HTU and NTU values. You need to know the contaminants in the water, and you need to know the analytics in terms of that. You need to know temperature, pH, all that stuff. So as far as the basics, basic efficiency, I can send you an email a little bit probably later that would be a little bit more thorough to than trying to tie up a lot of time on that, because that's a broad, kind of a broad term. So if you have a specific question in mind, if you can rephrase it, I'll try to answer it better. But can nozzles become clogged in high H2S application? Yeah, they can. And it also depends on the hydrogen sulfide and some of the other constituents in the water. If the nozzle, if the water has other elements in it, We've seen nozzles be plugged before with high hydrogen sulfide that are actually oxidizing even before it's getting to the distributor. And also if it has any kind of calcium or scaling process or biological process, that can actually help clean the hydrogen sulfide together. And but it's less likely and less common, I think, in the distributor, only because, like I said, most heterolateral distributors operate under a little bit of pressure, so it helps keep the solids buildup from occurring. And most of the nozzles are open hole type nozzles, so you don't see it very often. Next question, what's the maximum CO2 limit for decarbonator feed? So what is the saturation limit in treated water? Again, it's not a simple question because it's really temperature related. Colder water holds more CO2, warmer water holds less CO2. So as far as saturation limits, it's definitely temperature driven and can also be pH driven. The question, is a forced air filtered to a certain micron level? Is the forced air filtered to a certain micron level? If you're speaking about the forced air that's entering the decarbonator tower, there's several types. We have basically open air type, which are just screen. We have filtered air, and then we have filtered air all the way up to HEPA level filtration prior to entering the decarbonator. And quite frankly, I don't remember off the top of my head what the micron level size is for HEPA filter, but it's obviously gets down to the bacterial level size. So here's a new question. I just ordered a forced draft degasifier at a load rate of 10 to 11 gallons per square foot diameter. Does this raise any alarm bells? Application is only decarbonation. Well, again, if it was designed properly, someone is probably pumping more air into it. On the surface level, without knowing all the details, you probably could have had a smaller decarbonator to do the same job under a higher hydraulic load. Again, not knowing the temperature and the design parameters that you were given, but you should definitely look into the lighter load rate and the parameters on it to make sure you're going to get performance. But that is very light load, yes. My post-RO water pH is 5.5 and CO2 is 20 ppm. Atmosphere CO2 concentration is 400 ppm. Can we use degasification tower to decrease CO2? Yep, absolutely. If you've got a post 5.5 in CO2 and 20 parts per CO2, I don't know what the temperature is in your water or any other applications, but you can easily remove 99% on CO2 and drive the pH, like I mentioned before. You can get a 6.5 to 7 post-treatment after degasification tower. In what cases do you deal with chlorine in the water prior to treatment? Normally, if we see water feed at food processing plants and some industrial plants, if they're bringing in treated water from outsourced, in other words, not treating their own raw water, they're bringing in water that's been chlorinated for disinfecting purposes. That's the only time I've been involved that I've seen cases where they deal with the chlorine and do water treatment. We have a couple industrial processes on microelectronics on the east coast of Florida that we deal with this, and we remove chlorine prior to treatment for RO and for obviously for the microelectronics purposes. How do you solve fouling in towers? Well, that's definitely a multi-million-dollar question. Fouling in towers actually comes in different methods, really. You can have calcium carbonate, you can have iron oxidation, you can have iron bacteria, you can have hydrogen sulfide, and of course hydrogen sulfide bacteria. But the best way to solve the fouling in towers is through proper setup of the pretreatment on the water and the selection, as I mentioned in the webinar, of the tower. If, for instance, I know someone's coming to us and they have a high concentration of iron, for instance, as an example, and they're asking for a column packed tower, we'll try to educate the customer and let them know about the fouling problems and the frequencies that they may have foul packing, and then give them an option to go with a different type of packing and or even a different type of pre and post treatment on the degasification to prevent the fouling in the towers. You can't really do a whole lot other than that. Cleaning towers in place does not work really effectively, even though if it's a calcium carbonate, you can acid wash it and circulate it as long as the tower was designed properly to take the chemical washing. But without that, then you could just damage the tower. So it's typically best to remove the packing. Can you repeat the square against round tank applications? Okay, square towers basically allow you to put what was called structured packing. So slat trays, the PVC slat trays that I mentioned in the webinar, and I'm sorry I didn't talk fast enough for the last few slides, but what they do is they allow vibration, and the vibration on the PVC slats allow the fouling to flake off and to fall to the bottom of the tower where they can be easily removed without causing fouling on the packing itself. So square towers basically allow a structured packing, where round towers it's much more difficult to use structured packing. So usually you only use random packing on the round towers. In the early days, we used some structured packing on round towers, and it tends to be problematic for removal. Obviously, you have to take the whole tops off and the distributors out. That's the last question I think we have right now. So if you have any further questions, I think David will probably provide you contact information. Please feel free to email me, and I'll be glad to answer anything further.
Thank you, Tony. We had quite a few questions. We had other questions that weren't answered, but again, like Tony said, we'll answer by email. He will be given a list of all of the questions, including the ones that we didn't have time to cover. And if you have any other questions, contact Tony. When you get the PDF tomorrow, the next day, the PDF has his email address. So just to wrap up, David H. Paul Inc. has a 3-day high purity water treatment seminar that includes degas. We have lots of training. So whatever your water treatment training needs are, we can support you. We thank you so much for attending. If you wouldn't mind, as you exit, there are 3 polling questions that won't take very long, but it gives us valuable feedback. So thank you so much.
Thank you.